Okay, so this is our last video of our set. This one's on implicit differentiation. Before I get to this one, let's do a quick review of what we've covered in this section. Our first day, we talked about what derivatives were. And a derivative, as I've said so many times through this video set, is the equation which provides the slope for the function that you were looking at. So if you had a linear function, the equation would be literally the equation of the derivative would literally be the slope term, right? If you had, let's just do one right here. Here's a linear equation here. If I were to give you the equation y equals 3x plus 2, the equation of the derivative, f prime x, would be 3, because the slope on this graph is always 3. Okay. And hopefully you'll recall that I've shown you many examples of why slope is relevant. Anything that involves a graphical analysis, for those of you who take the sciences. If you've taken my science classes, in my labs, I almost always give you a graph of some kind, and typically the slope is relevant to something. So anyways, now the slope of a linear graph is one thing, but what if you have the slope of something that is, it's going to curve around a little bit? Now this is a sinusoidal graph, but I mean, hopefully you'll see that the slope at this point here is very different than the slope here, is different than the slope here. So again, that's your derivative. Your derivative is the equation of the slope at a given point. When you plug in the x value into your slope, when you plug the x value into this slope equation here, it'll tell you that slope. Now, one thing we've been working on then is to learn what those derivatives are. And then we spent 4 lessons talking about different ways to find derivatives, because the first way that we found derivatives was using this formula here. The limit as h approaches 0 for f of, let's go with x plus h minus f of x over h. And sometimes this is known as using the first principles definition. And this one works. This is where you have to use limits. But there are faster ways, much more efficient ways. So the things we learned were the first day we learned about the power rule. Then we spent a day talking about adding and subtracting, a day on multiplying and dividing, and a day on how to deal with composite functions, which is known as the chain rule. Today, I want to focus on how to derive things that are not necessarily functions, and that's where we're going to begin here with this definition on the page here. So a function is an equation that has one output for every input, and hopefully you guys at one point in your lives learned about, say, the vertical line test, where if you draw a straight line up and down, a vertical line, and you slid that vertical line, like I can here with this pen here, across the paper, hopefully it only ever touches once, and it doesn't cross twice, which means that for one x input, you're only going to get one y output. However, we need to start talking about things that aren't functions. And for the most part in high school math, we don't focus on anything that's not a function. We talk about polynomial functions to begin with, your linear, quadratic, cubic, quartic. Then, at least in my course, then I start teaching about the radical functions, which are square roots, the rational functions, which are fractions, exponents and logarithms. Then we get into the sinusoidal functions, so sine, cosine, tan, cotan, secant, and cosecant. And then we kind of stop there. That's the end of your Math 30-1 curriculum. But the truth is that there are more than just those. It's just they don't happen to be functions. And there's an entire branch here of things that we term a relation. A relation is an equation which is basically just like a function, except it can have more than one output for every input. Basically, these are the things that are not functions that we've just ignored for the last, 4 years of your math education. And here's a really example of something that's a function. This one here that is a heart. It's possible to graph this, but right off the bat, look at this vertical line that I stole from above. If you plug in x as 1, you're actually going to get 2 different y coordinates. If you plug in x as 1, apparently y is either 0 or 1. And that causes a bit of an issue then, because now you don't have a single one-to-one relationship, which is what defines a function, right? A function is defined by that one-to-one relationship. So one of the things that you'll notice if you were to zoom here on in the equation is that these things right here are usually characterized by the fact that you have x's and y variables, which, I mean, isn't new. We always had x's and y's. But the difference here is that y is not going to be isolated. You have multiple x's. Right? It's subtle, but there's an x right there and an x right there. And you also have multiple y's, which is going to make it very challenging for you to get y by itself because, I mean, if you have more than one of them, then how are you going to get just a single one so that you can write it in the form y equals something? And so that's what we're going to work on today is how do we derive something that has multiple y's in the equation. Hence the lesson that we're going to do on what's called implicit differentiation. Okay. Here's a slide I threw in here just to remind you of all the different types of functions that you may or may not have learned about, right? I kind of gave you a list of things you should have learned before. When I teach my students, I break them down into 3 categories. You've got your polynomial functions, then you've got what I termed as your non-polynomial functions, which include your square roots, they include your fractions, your rationals, they include your exponents, and they include your logarithms. Those are kind of your main 4 non-polynomial functions. And then you've also got to cover anything that's in your trig section. So that'll be like trig will cover sine, cosine, and tan and cotan. Really, the absolute value probably could go in your non-polynomial functions as well. X and x squared are going to be your polynomial functions. These 3 guys right down here are going to end up being your non-polynomial functions. But this guy right here is the one I want to focus on. This is like in the Sesame Street game, which of these things is not like the other one? Which of these things just doesn't belong? I mean, other than the silly one at the end there where he goes, oh crap, I tied my hands together. Really, this one that I had drawn right up here, this one here is the one that doesn't belong because it's the one that's not a function. You have x squared and you have y squared. And as soon as you start doing things like squaring your y values, it usually means that you're not going to have a function anymore. And so hence I think I've done my preamble enough here. This is what we're going to work on. So let's start with just a basic premise of how this will work. If you want to graph a circle, this is actually the equation for a circle. You go x squared plus y squared, and it equals a number. And this is actually the graph of a circle where this number right here is really, you could treat 9 as, say, 3 squared. 3 actually happens to be the radius of the circle that you plot. And so this is now a new function that you probably haven't seen before. Maybe you have. Right? And it works like this. X squared plus y squared equals 3 squared. And then you can do things like throw some coefficients in front, and it changes it from being a perfect circle to maybe being like an oval or an ellipse. But this is kind of one of your general non-functions. In the previous curriculum, before they changed it to Math 30-1 and 30-2, we used to actually cover these. So there used to be a section that, I mean, first you started with all your functions, your polynomials, your non-polynomials, like say your exponents and logarithms, then your trig functions, and then after that they continued on into your non-functions. So, by the way, I should point out that even in terms of the units that we're doing here, we've more or less been focusing up till now on your polynomial functions. Our next unit will be on things like trigonometric functions and exponential and logarithmic functions. So we're actually going to focus on those next, just so you guys are aware. So, here's another cool example of something that's not a function. This is called and I hope I don't butcher the name, it's a Scherhausen cubic. This is one of my favorite looking graphs. It kind of looks like an alpha symbol, if you know the Greek symbol for alpha, like if you do physics and you know, like, this is an alpha particle with like a 4 and a 2. Anyways, I like this one. This one's kind of got like a fish shape to it. And again, you can see that this totally fails the vertical line test right here and here. And equationally, one of the reasons why is that as soon as you get a y squared, it fails the vertical line test. Now, if you want to know why it fails the vertical line test, one of the best ways that I can explain this is that if you were to square root this function right here, and you were to square root this function right here, one of the things we know is that when you square root, there is both the positive and negative part of a square root, which is something that we've already seen in, say, the quadratic formula. In the quadratic formula, all square roots, this is a good example of how there is the positive and the negative half of the graph. Well, this blue one right here, say, could be the positive half of the graph. And then this red one here is its vertically flipped side, which is the negative side of the graph. Okay, so let's talk about how to do implicit differentiation then. Basically, the idea is that we're going to treat derivatives just like it's a mathematical operation. You know, like say when you can multiply both sides of an equation by 2, or you could add 7 to both sides of an equation, right? Like here, let me just give you a quick example. If I gave you 2x plus x, and I told you that it was equal to 3x, if you wanted to, you could divide both sides of the equation by 7. That's mathematically valid. You could add 3 to both sides of the equation. That's valid. You could take the logarithm of both sides of the equation. That's valid. So what we're going to do today is we are going to differentiate both sides of the equation with respect to x. And it's actually going to end up requiring some chain rules when we differentiate y terms. And that'll actually help us get our derivative. So why don't I just hop into an example now that I've done quite a bit of talking. So here's our example. We've got x squared plus y squared equals 25, which you can't really graph this on your calculator quite as well. So you just have to know the shape of this. This is going to be a circle. And the circle is going to have a radius of 5. So, like, for example, you'll have the point 5, 0 on the graph. This will be the point 0, -5 on the graph, and so on. Okay. And we're being asked to find the slope of the tangent line. And here's a little bit of a different thing here. It's actually going to give me an xy coordinate. And that was actually the reason for this was on the previous slide. I kind of skipped over reading it. But if I just told you that x was -4, -4 is right here and right here. Right? Here is where -4 for x is. And so I have to be more specific because here's a tangent right here, and there's another tangent right there. So I actually need to know which one of the two we're going to do. And it says that we're going to use the one at 4, 3, or -4, 3. So it means that we're using this one here. All right, that'll be -4 with 3. So, okay, so let's show you how you do this. What we're going to do is we are going to, using implicit differentiation, we are going to derive both sides of the equation, kind of like when we add 3 to both sides of the equation. So it's going to look like this. D over dx, we are going to derive x squared plus y squared. And then we are also going to derive the number 25. Okay, so when we do that, one of the big changes here is that normally we might write the notation, like normally I've been writing notation before as like say dy over dx. But the issue with that is I don't have an equation that has y by itself, right? Like if I knew that the equation was y equals 2x plus 1, I could write it as d over dx and then replace this y with 2x plus 1. But the difference here is that I don't actually know what y is equivalent to because I don't actually have y by itself. Now on this one you might argue, well, Chris, just subtract the x squared to the other side, square roots, and that there's some possibilities there, but as these get more and more challenging, that's not always going to be possible. So implicit basically means take the equation as written, the x squared plus y squared equals 25, and derive both sides with respect to x. Okay, well, I mean, now according to our addition rule, this guy really means here, take the derivative with respect to x of x squared, and then add to that the derivative with respect to x of y squared, and then that'll equal the derivative with respect to x of 25. So I actually have to take 3 derivatives. Now, of these derivatives here, 2 of them are drop dead easy, hopefully by now. This first one, for example, what this says is take the derivative with respect to x, meaning that you have to have x variables of x squared. You say, well, I have x variables, I can do this, so it's 2x. And over here, derivative with respect to x of 25. Now, you might be tempted to say, oh, I don't have any x's, I can't do this, but actually you do. You have x to the 0. I mean, we don't usually write that x to the 0 because it's a little bit redundant, right? But remember, this is the graph of 25. Right? Literally, this is a y graph, and way up here at 25. So the slope of that is indeed 0. So those 2 are the easy ones. This one over here is a bit more challenging, though, because what I've asked you to do is take the derivative with respect to x, but we actually have y as the equation. Now, when we came across this conundrum yesterday or last day, whenever it is you watched your chain rule video, we sometimes replaced y with u. I'm going to kind of do a similar concept here. The way the chain rule works then is that we have to recognize that y does equal something. We just don't know what that something is, but really there is a something. If y could be gotten by itself, it could be in theory be equal to some sort of u. So what we did last day is we just derived the u. I gave the analogy of this is a pregnant mom with a baby inside. You derive the mom, keep the baby inside, and then take the derivative of the baby. So here's how this would look. You're going to do 2y to the 1, because really you're going to drop the 2 down in front. You're going to drop the 2 down to an exponent of 1, and then y, the baby inside, remains there. But then you have to times by the derivative of the baby, which would be the derivative with respect to x of y. Well, now I want us to consider a little bit of the notation. When we're solving for something, I mean, often I write it as f prime x, but another way of writing it is dy over dx. And this is the notation that we give to something that has been derived. I say dy over dx is equal to, and then I give you an equation. So what we're really looking to do now is take this thing right here, this dy over dx, and we're going to isolate it as though essentially it's a term. I want to get it by itself. So the way that would look is I'd still have 2y times dy over dx, and I'm going to bring my 2x to the other side and make it minus 2x. I'm going to swing that guy to the other side. And then to isolate the dy over dx term, I'm going to divide by 2y on both sides. And what I've now found is that dy over dx, the derivative of y with respect to x, is now going to be negative y over x. I have an equation that will give me the slope, right? And I mean, think of a graph. Graphs are always y and x axes. I mean, it just so happens that it now loops around in some sort of circular format, but that's fine. But you know what else is unique about this is if I want to find the slope at a certain point, like say this point right here, I don't just need to know the x value, but I also would need to know which y value it was. Because if you remember the actual graph of this here, if I plug in x being negative 4, there was actually 2 possible locations where it's negative 4. So I actually also need the y value. So if I want to find the slope at the point I was given, which was negative 4 and 3, now I can plug in negative 4 for x and 3 for y, and I know that my slope was 4/3. So this is a bit of a change. This is a different mindset. The idea is treat derivatives like terms and treat the derivative concept similar to adding or multiplying or dividing or taking a logarithm. If you do it to both sides of an equation, then the equation is still mathematically valid. And so what we're going to do is we're going to isolate for any dy over dx terms that you may discover. So you may want to rewatch that and see whether you can pick up on any subtle little things you missed the first time around. I'm going to move on to our next example. This is actually a fairly short section of notes. I've actually shown you the concept, but like I've been kind of bugging you with all this unit here, you need some practice on this. You can't just watch it once and go, yeah, I got it. So let's try this one. We're going to differentiate this guy. And the difference on this one here compared to the last one is there is no way to isolate for y. You cannot get y by itself. You might be able to, at best, factor a y out of this side right here. But even if you got y by itself, you'd still have y as part of your equation, right? There's no way to purely isolate for y. Hence the need to do this. We're going to take the derivative with respect to x of the 3xy minus 2y squared. And we're going to take the derivative with respect to x of 5x. And the reason why this works is because we're essentially doing a mathematical operation on both sides of an equation. Right? Another reason why I love Leibniz notation, because now I'm going to pick through and I'm going to find derivatives that I can take. For example, over here on the right-hand side, I can derive d over dx of 5x. I mean, here's another way of approaching it. You could consider this to be d over dx of 5x. Why don't I put the 5 here and put the x there? Wouldn't dx over dx basically be equal to 1? Doesn't it make even intuitive sense that the slope of 5x, the slope of that is 5? Right? The way this notation was developed is very clever. Well, over here, I need to take the derivative of both terms. I got to go 3xy, and then I also have to derive 2y squared. So I still have 2 more derivatives to take. And this is where we're going to have chain rules and product rules come in because, I mean, just for this guy right here, this is a product rule. I have 3x being multiplied by y. Right? Think of it as this is one portion of it, and this is the other portion. So according to my, this is a product rule, that one is the first times the derivative of the second plus the second times the derivative of the first. Right, well, that just takes care of just this bit right here. Why don't I use another color to separate here? Then I still have to deal with this guy's derivative. And this is going to be a chain rule. I'm asking you to derive something with respect to x, but there are no x's here. So the way the chain rule would work is pretend that y is the baby inside the mother. The actual function is 2 something squared. Well, to derive 2 something squared, it becomes 4 something, right? The 2 drops down to a 1. I won't even bother drawing the 1 here. And then the baby stays inside, but then you have to take the derivative of the baby. Okay, we still have another derivative left to take. This guy right here is actually what we're looking for. That's dy over dx. And this guy right here is also what we're looking for, which is dy over dx. But this guy right here still requires some more deriving. So I'm going to clean this up a little bit here. This is going to be 3x times by dy over dx. And then this is going to be 3 times y, because really all of this right here, the derivative of this is 3, but there's that y in front. And then I'm going to minus 4y dy over dx. That's going to equal 5. Now this would be a stage here where if I were teaching in a normal classroom, I'd be pausing quite a bit, waiting for kids to process and ask me some questions. And I wish I could be there right now to answer your questions, because this is another big step up from where we were a little while ago, where you have to go, whoa, what just happened? So if you're able to follow that, that's great, but you may want to rewatch the video and make sure you have some questions waiting for me. Okay, so next thing we need to do then is we need to isolate for our dy over dx signs. And one of the ways I'm going to do that is I'm going to combine them all on the same side of the equation and bring everything else to the other side. So I'm going to keep the 3x dy over dx on this side of the equation. I'm also going to keep the minus 4y dy over dx on this side of the equation. On the other side is going to be the 5, and I'm going to subtract 3y because I'm going to bring this term the other way. Then, now that I have all of my dy over dx's on one side of the equation, I'm going to factor them, which is going to give me dy over dx bracket 3x minus 4y. And the reason I'm going to factor them is that now I'm able to divide away that excess remaining bit, the factor. And now I've gotten to the point where I now have a derivative. I have dy over dx, which really that is another symbol for a derivative. And I found what it's equal to. The derivative is equal to 5 minus 3y over 3x minus 4y. If you want to find the slope, you do need to know both x and y values to do so, but this is now an equation that will get you that slope. So let's talk through some of the key components of this, because you guys can rewatch videos here. Some of the key components are you need to be able to recognize what sort of derivatives are happening. In red right here, this guy needed to be a product rule. This guy needed to be a chain rule. And this one just derived fairly normally. At a certain point, maybe I'll use a highlighter here if I can. Maybe I'll use this pink pen. At a certain point, I got to a spot where I had some dy or dy over dx's in a few different locations, right? I had them here, and I had them here, I had them here, and I had them here. And I had to combine them into a single dy over dx, which I did by doing some factoring to get to this guy here. Well, this is what you're trying to isolate for. Consider dy over dx to be your derivative. That's what we're solving for. Now, some teachers and some people will actually just write it as y prime. They'll write all of the dy over dx's as y prime. I suggest not to do that. And probably don't do it in yellow either, because I can hardly see that. I don't know about you guys. Let's do that in new color. Let's do that in green. You could write dy over dx as y prime. But I don't like that because sometimes I think of, when I see that y prime, I might think that it's y to the power of 1. Really, that prime symbol should be italicized and written a little bit sideways. And boy, there's a high likelihood you're going to make a mistake if you write y prime instead of dy over dx. So this is why I encourage kids, get to use your d over dx notation. Learn your Leibniz notation, because he did a great job of finding a good way to keep track of this. Right? When you're done and you have your dy over dx variable, then there's your answer. Okay, let's try another one. I'm just going to example you to death today. I've only got 2 more examples, and then that's actually it for our whole unit and section. Kind of halfway done the course after this. So make sure that you pause and you ask me questions. Make notes of things that you didn't fully get, just so that I can try to try to help out with that later. Okay, so I'm hopping right into my first step. I'm going to take the derivative of both sides. And really, this derivative right here means that I can do it for all three of them. So I can really do the derivative of 2x to the 5. I can do the derivative of x to the 4y. I can do the derivative of y to the 5. And this one right here, why don't I take this derivative right off the bat? Because the derivative of a constant term is 0. So there, I'm done with this derivative. Sadly, I picked up 3 more over here. One of them is very easy to deal with. This first one is 10x to the 4. That one was easy to deal with. The problem is this second one involves another product rule. There is 2 terms being multiplied by each other. So it can be written as, say, the second times by the derivative of the first plus the first times the derivative of the second. So that takes care of the middle guy. And then this last one here, anytime you have a y as your derivative, you have to treat it like a chain rule. So pull the 5 down in front, make it y to the 4, but we don't know what y was equal to, but it's certainly y is not x. And so because we were deriving things with respect to x, but we were using y, we're going to need to chain on an extra derivative of that baby, which is good, because really this is the thing that we actually want to isolate for. And you may notice that I actually have 2 of them. One of them I literally wrote right here like this, but there actually is a second one right there. I wrote it just off to the side, the y, but hopefully by now you recognize that I've been treating that really the same thing. The problem is I'm still not done yet. I still actually have to take one more derivative right here. So sadly I have one more line of work I got to fill out. So let's just write u the same. Let's write that the same. Deriving x to the 4 really means you got to go 4x to the 3. And then yeah, I got to keep all of the rest of this stuff the same. Right, now this dy over dx, you could call it y prime. I don't like to, because it makes me think that I have y1 there. So as soon as I was shown Leibniz notation in university, I was like, wow, this is brilliant. My high school teacher actually didn't teach me Leibniz. He taught me how to use just y primes and f prime x's. As soon as I got the hang of the dy over dx bit, I thought this was way easier. And so I always show that to kids. It's a little intimidating because, I mean, they look at it and they go, whoa, there's extra d's in there. And sometimes kids think, hey, why don't I just cancel the d's? But that's not really what this notation means. It doesn't really work that way. But if you're not intimidated by it, it's a much more powerful way of trying to solve. So at this point here in my classroom, I'd ask kids, well, how many derivative symbols do we have? And hopefully you'll say, well, we have 2 of them. So I'm going to do a couple of steps in one now. First thing I'm going to do is I'm going to factor out that derivative symbol of the terms who actually contain it. So the x to the 4 contained a derivative symbol, and the 5x to the 4 did as well. The other terms I'm going to bring to the other side of the equation by subtracting them away. So I'm going to need a negative 10x to the 4 on the other side, and I'm going to need a minus 4x to the 3y. I'm just going to rearrange this term slightly. And then lastly, I divide both sides of my equation by the factored component to give me a derivative of this. That is my y prime. If now I want to write it as y prime, that's probably fine. But whenever you have these dy over dx's right here, I think it's highly dangerous to write that notation. Really, all of these 3 things here mean the same thing. Y prime means f prime x means dy over dx, but just this notation, like I've been hinting at over the last couple of lessons, I love Leibniz notation. I think it makes it very clear what you're doing. And I think I said this in the last video. If you've learned anything in grade 12 math, it's that your ability to notate and keep track of what you're doing is super important. All of the little details make a difference. Sine squared x is not the same thing as sine of x, squared necessarily, right? Really, it's actually that, where it's squared. That one little bracket makes a huge difference. Notation like FOGX, knowing what that means, meaning that really means F bracket G bracket X. And even then, knowing that this really means to take a G function and substitute it into the X value of an F function, right? Knowing what all this notation means, that's super important. So, okay, rewatch that video, make me a list of questions to ask me. I'm going to do our last example, then I'm going to talk about our midterm. Okay, so this last one here, I'm going to skip down and do a couple of steps at once now. I'm going to go right to the point where I'm just going to start differentiating all of our terms individually. So I'm going to take the derivative of the x squared. I'm going to take the derivative of the y to a half. Hopefully you caught how I pulled that one off. I'm going to take the derivative of x squared y to the 3. And I'm going to take the derivative of 5, all with x as my variable. So anything that actually has x as the variable should be easy to derive. Like, say, the first term. This one's done. It's 2x. Ta-da! We're finished. The second one, however, is a bit trickier. It is a deriving with respect to x, but we have y's. So we do 1/2 y to the minus 1/2, and then we chain on an extra dy over dx derivative, which is good. It's actually a good thing we have that, because that's what we're going to solve for when we're done. Now this guy here is a product rule. So formula for product rule is, what do? We do the second guy times by the derivative of the first guy plus the first guy times the derivative of the second guy. So that takes care of the product rule for this one. And then lastly, I take the derivative of 5, which is 0, right? There's no slope to a graph on 5. So I've done fairly well. I've gotten rid of a couple derivatives. This is what I'm trying to solve for, so that's good news. But I actually have a few more derivatives I have to work with. So you can see why you're going to have multiple steps, many of which really just involve dictating what you previously had written. So make sure you don't make a mistake writing things down from the previous page. Okay, I'm going to derive x squared. That'll give me 2x. And then I'm just going to combine it with the y to the 3 that's already there. And then on this next one right here, this is another chain rule, so I'm going to bring the 3 down in front. Then the y will then go down to a y squared. So really, I brought the 3 in front of everything, because it's going to times by x squared, right? So this is actually 3y squared. I just put the 3 in front. But you still have to times by an extra dy over dx derivative. And then there's no point in writing plus 0. One of the things you'll discover after a while is anytime you derive a y, any y, you're going to get an extra dy over dx derivative, which is awesome. We want those. So now we just need to isolate. I have 2 of them. There's one here and there's one here. That's what I want to isolate for. So I'm going to bring them to the same side of the equation. So I'm going to do it this way. Minus 1/2, or 1/2 y to the minus 1/2 dy over dx. And then I'm going to subtract 3x squared y squared dy over dx. So I'm bringing this guy to the other side. It's going to equal to 2x y to the 3. And then I'm going to bring the 2x the other way and subtract it. And then once you get fast at this, you can kind of get a little better at seeing how you're going to factor. I'm going to factor out the dy over dx. It's going to involve leaving this guy minus this guy, which will then get divided off the bottom of the other side. So I'm just going to skip one step, just because you are going to have so many steps to work through. And I mean, if you can do it in your head, just this little one step right here, I'm okay with that to some degree. I mean, don't get too ambitious. I usually recommend, when it comes to doing your product rules and your chain rules, don't try to do this bit in your head here. Do that all step by step, one at a time, just to make sure that you don't accidentally miss taking a derivative or you don't forget a chain rule. But I think down here, this is a reasonable thing where if you can see the algebra part here in your head, go ahead and factor out the dy over dx, leaving you with this stuff left over, and then just divide it to the bottom of the other side of the fraction. Here is our derivative then. Okay, so we are done our set of notes. It's a little bit shorter perhaps than what some of our other ones have been. My running tally says we're at 34 minutes, which is about right. I recommend watching this video again. And truth be told, I actually recommend watching pretty much all of the videos in this section at least twice, probably more. This is one of the advantages to a VC course. You can rewatch this as much as you like. Downside is you don't get a lot of teacher support. So you need to be the ones to actively engage me. I promise you, I will help you by email, by video conferencing, in person if possible. But I can't chase you down. I physically can't. You live through a computer screen to me. All right? So if you don't reply to my emails, I can't help you. And right now, you need some help. Not because I don't trust you or believe that you have the ability, but you have a midterm coming up, and you need to start prepping for it. So the advice I would give is get working on that assignment as soon as possible. Ideally, in our 3-week stretch of time, ideally you would be watching this video on week 2. That's what I'm going to advise you in the email I send out. But hopefully you're not watching this on, like, say, the Thursday of the week the assignment is due. Because if you're doing that and you're procrastinating, I mean, maybe you'll do well in the assignment. It's possible, but you're really digging yourself into a hole. So stay ahead of the game, right? And hopefully you can get that assignment done as soon as possible so that you can get it submitted. And I'd love to get you guys feedback. My struggle has been I can't give back assignments till everybody's handed them in. But hopefully I can give you some feedback where I can tell you, yes, you're doing this right. Because, I mean, here'd be the worst thing. You've spent your whole 3-week period doing this assignment. You're doing it wrong. And so then you tank your assignment and you have no time to get ready for your midterm. And then you tank your midterm too. Because really, between this assignment and between the midterm, you've got 35% of your mark coming up here. Right? Your midterm's worth 30%, and each assignment is worth 5%. So this is a pretty valuable section here. So, okay, let me talk about your midterm for a bit here while I can chat over a video thing here. Your midterm is going to consist of, I believe, 10 questions. I got to look it up. And it's designed to be done in basically 2 hours or so. I'll give your administrator, whoever in your building is your admin, I'll give them the test, and they'll administer it. And it's going to be up to you to find a period of time to do that, which may be a bit challenging. You may have to stay after school, or you may have to write during lunch hour. But you're going to need to try to find a 2-hour or so, maybe even longer than 2 hours, but a 2-hour block of time to write this. Because you can't do this in 45 minutes. That's not going to be possible. I can't test everything I need to in a short period of time. So you find a way, and you set it up with your administrator as to when you're going to write it. And basically my only rule is I need it done by the end of that week. So the week that we're having for midterm week, you can write it on Monday or Tuesday or Wednesday or Thursday. I mean, I'd recommend trying to set it up with your admin to write it on probably the Wednesday, Thursday, or Friday so that you can spend the earlier part of the week studying. I do textbook questions. Find a workbook. Email me. I will find you questions. You can find worksheets online. But you're going to want to do some prep work if you just do the assignment as your prep for the midterm. I don't know how well that's going to go for you. So, and make sure you're in contact with me. Email me. Let's VC. Let's chat. Let's find a way to get you some feedback so that I can make sure you're doing this properly and that you're building skills well. So, but anyways, when it comes to that midterm, yeah, it's worth almost a 30 a grade, and it's on everything in the course so far. So go back to even topic 1 in the pre-calculus unit, because those skills are still needed, right? Even little things like rationalizing denominators and domain and range and interval notation. I'll still assess you on that. Limits obviously are a big part of where we built to in derivatives. And then, yeah, there's going to be obviously some questions on this derivatives as a main focal part of your midterm. So please email me your questions about what to prep for on the midterm. I'll give you some things to prepare for. I'll give you some ideas of what sort of questions you'll get. And then, yeah, you have 1 week to write it. You got to write it sometime during that 1 week period. You make the arrangement with your admin, and then they'll mail me your test, and I'll mark it and try to give you some feedback. So, okay, I think I'll end the video for now because I've more or less been talking at a blank screen for the last 5 minutes. Get a hold of me, guys. Make sure you ask me lots of questions. I am here to help you. So make sure you take advantage of that. If you try to do it by yourself, it may go okay, but I mean, that's not the point of this VC school, right? The point of the VC school is to utilize your teacher. So let me know how I can help you. Send me an email, talk to me over VC, find me in person. Otherwise, we will talk to you guys later. After your midterm, we're going to start some videos on the second half of our year. So good luck, everyone.